I just realized I forgot to turn on the recording, so the first section didn't get recorded. I don't know if any of you noticed, but I have been putting the recordings on the class webpage, except for the one where I forgot to screen share, because the recording is really just audio, but I thought I could fix it by, manually splicing in the slides. Problem is, that's pretty laborious. So it's taking me a little bit of time to get that one ready, but okay. So for the moment, right now, the agenda is to talk about deterministic concurrency and look at a variety of different ways of achieving it and look at what their properties are, okay? And there's whole communities around these. I should tell you a little bit about why I feel qualified to talk about this. Because for many years, exploring these ways of doing deterministic concurrency was the main mission of the research in my group. And we built this system called Ptolemy 2 specifically to facilitate experimenting with concurrency models. That was its goal. So the goal of the Ptolemy system was to be our laboratory for experimenting with ways of doing concurrent and distributed software. And so Ptolemy 2 is open source software. You can download it and you can, experiment yourself with these, this, full rich set of possibilities. So let's start with Dataflow. And again, just as a matter of background, I actually did my PhD thesis on Dataflow models of computation way back in 1986. And I developed a technique that is called Synchronous Dataflow. And it's one of those misuses of the word synchronous because it has a different meaning than almost everyone else's definition of synchronous. But I'll explain to you what it means in that context. Okay, so Dataflow has a pretty long history. A lot of people credit Jack Dennis with having kind of originated its use as a model of computation, but it dates back, it's traceable even further back to Dick Karp way back in 1966. And at that time, these guys were thinking of it as an alternative for an alternative principle on which to build microprocessors. They were thinking of it as a technique that would be used at the architecture level, in fact, at the microarchitecture level, and they would build hardware that used this Dataflow principle to execute programs in much more parallel form than the von Neumann machines that we've all become familiar with. In fact, there was a whole slate of startup companies around Dataflow machines way back in the late 70s and early 80s, and they all failed. None of these architectures ever caught on, but there was a lot of work on that. By the time that I started working on it, I was not focused on using it as an architectural technique, but more using it as a software technique and as a software architecture. Although the work was still pretty low level. If you go back and you look at my thesis, you'll see that we were compiling Dataflow programs directly into assembly code for very highly specialized processors. So it was still working at a pretty low level. But long history there, and it has really, I sort of ran out of room in 1997 on this slide, but it's, there's still papers that are being published on various twists and turns on the Dataflow model of computation. So the basic principle behind Dataflow is that you have a bunch of components that have associated with them firing rules. And so the component is a chunk of computation that fires. And it maps inputs to outputs. And the firing is thought of as instantaneous. And then the rules govern when the firings can occur. And the firing rules are about the availability of inputs. Okay, so in particular, and if you have a data flow actor with no inputs, it can fire at any time. So you fire it, it produces outputs, and those outputs then potentially enable other actors to fire. Whether this guy is enabled right now depends on your firing rules. Okay. If your firing rules are such that it can be enabled by a token on either input, for example, then it's enabled. If your firing rules require a single token on each input, then it's not enabled. Right? So you have these firing rules that are all about just counting tokens. There's no timestamps here, right? It's just the availability of tokens. So if the firing rule for this guy, for all of these, so the synchronous data flow model, the one that I used in my PhD thesis, had a very narrow definition for what the firing rules were. They're very simple. Each input has an integer associated with it, which is a specification of how many tokens are needed to enable that. So in this case, for example, this firing rule says that this actor foo can only execute if it has a token on each of the two inputs. One token here, one token there. And then it can fire. Okay. So in this case, only Baz is enabled. It fires, produces a token. At that point, another requirement of the synchronous data flow model is that when an actor fires, it always produces an integer number of tokens. Okay. And then, so as a consequence of that, the pattern of firing is very predictable. Right. So this is a particularly trivial case, but there's much more interesting cases, as you can probably well imagine. So if you're curious, one of the things that I did in my PhD thesis was show that for arbitrary collections of integers that you could put associated with these firing rules, you could write down a system of equations that either had no solution, in which case the system was unbalanced and could not be executed with bounded memory, or it had an infinite number of solutions, and there was always a least integer solution. And in that circumstance, it could always be executed with a bounded amount of memory, and you could construct a schedule to execute it, and you could parallelize the execution. Okay, so that was sort of a quick thumbnail outline of core results in my PhD thesis. That led to a bunch of follow-on work, including a whole book on scheduling strategies for these synchronous data flow graphs. This is a particularly simple example of a synchronous data flow graph. And because these integers are all one, this ends up being a system of equations that involves 3 equations and 3 unknowns, and it has solutions, and it has a least integer solution. And the least integer solution tells you that you can construct a schedule that consists of one firing of this, followed by one firing of this, followed by one firing of this, and then you can repeat that forever, and you will never run out of memory. Okay, so for this simple example, solving those equations, which we call balance equations, is really quite straightforward. But in general, the solution to the equations can get rather intricate, and the scheduling problems can get very interesting. And there were a whole bunch of PhD theses written about this. So a lot of elaboration. Yeah, if you know execution times, you can also come up with throughput and latency bounds. But the problem with that model of computation is that it's really very limited, because the behavior of these data flow actors is very rigorously defined ahead of time. And in fact, the model of computation is not Turing complete. In fact, the fact that you can determine whether a program can run in bounded memory is sufficient to prove that it's not Turing complete. Okay, which means there are computations that cannot be given in that model of computation. Computations that are legitimate Turing church computations. Okay, so it's a limited model of computation. It has limited expressiveness, but you can generalize it. For example, suppose that this actor, its firing rule is that it's enabled by a single token, but it may or may not produce an output token. Okay? Maybe it does, maybe it doesn't. It checks some condition. So there's a generalization of synchronous data flow called Boolean Dataflow that associates a symbolic variable here, B, that can have value either 0 or 1. Right? And correspondingly, you have a firing rule here that uses the same B, okay? Meaning that if this guy produces a token, then this guy will require that token in order to fire. Right? So now you can write down the same system of equations, but now it has symbolic variables in it. You can symbolically solve this equation or show that it doesn't have a solution. Okay? Or you can show that if, for example, this had a different variable Q that didn't have any relation to B, then you could show that there are assignments of values to B and Q such that the program will require unbounded memory. Okay. But you can write down this system of equations symbolically. So that was an extension of this model that we did in 1993. And quite surprisingly to me, my PhD student, Joe Buck, showed in 1993 that this simple addition to the model was enough to make the model computation Turing complete. Okay. Just by being able to have Boolean variables specifying whether the whether a token is produced or not. Okay, and as a consequence, he showed that the scheduling problems in general are undecidable with this model of computation, meaning, for example, that if you want to answer the question of whether a particular program can execute in bounded memory, you can prove that there is no algorithm that can always answer that question for any program. Okay, that's what it means for it to be undecided. So that work led to a whole flurry of work, mostly done by other people outside my group, who were trying to enrich the synchronous data flow model without making the scheduling problems undecidable. Okay, they wanted to keep some constraints, make it more expressive, but not so much more expressive that you lost the key advantages of being able to analyze the programs. And so here's a few of those extensions: cyclostatic data flow, which came out of Belgium; scenario aware data flow is quite nice, coming out of the Netherlands. Let me explain that one briefly. So there, these guys associated with the data flow graph a state machine, a finite state machine that governed the switching between the variable assignments for these variables. Okay. And that trick alone was enough to keep everything decidable for this framework. All right. And it's also, it's quite practical. I mean, it turns out this is really quite expressive compared to synchronous data flow. You can design much more complex programs. And they have continued to elaborate that work in various ways, but I'm not going to go into the full detail there because it would take me quite a long time. So what I'd like to do is then give you a related model of computation that has some rather different properties, which is process networks. And these are originally due to Gilles Kahn, who was at INRIA at the time in France. And the networks of such processes are now known as process networks, or KPNs. And the way that they work is you have some component that has, say, 2 input streams, and the process network is a process that runs forever, and it does these blocking reads on the inputs. All right, so what this means is just an imperative program. Okay, when you hit this read statement, you read from this input. If there's no token there, you just wait until there is a token. Okay, that's what's meant by a blocking read. And then when you get a variable there, you can use its value and continue executing. And then here you do another blocking read on this guy, and then return back to the original. So here's so first of all, I'm trying to give you sort of a rapid tour of a bunch of models of computation, but this is much deeper than it might look initially. So when Gilles Kahn first proposed this model of computation, he did it in a very, very short paper, 4-page paper in 1974. And the paper is an absolutely beautiful piece of mathematics. It doesn't talk about blocking reads at all. It talks about monotonic functions in a rather weird topology. And it talks about fixed point theorems on those functions. And it proves that any composition of processes that implement these monotonic functions is deterministic. And deterministic in a pretty interesting way. What he meant by deterministic was that if you had a network of these processes like this, okay, that the program defined exactly one sequence of messages for every connection. Could be an infinite sequence. In fact, typically it is in Kahn processing. Okay, but the monotonicity of these functions, this turns out in his formalism is a function that maps a potentially infinite sequence of messages into a potentially infinite sequence of messages. And the notion of monotonicity here is pretty subtle, and it's related to the concept of causality. At an intuitive level, it kind of means that the function can't produce an output that anticipates future inputs. Okay, and that becomes the monotonicity requirement. It was later, 3 years later, that Kahn published a second paper in 1977 with a fellow named McQueen, where they introduced the blocking reads and showed that any process that was implemented with blocking reads was monotonic in the sense of the original paper. And so you could accomplish Kahn process networks by using these blocking reads. That led to a whole bunch of theory work as well. One of the people who was kind of my mentor in learning all about this was Gerard Berry. And he discovered that there was this really weird class of processes, of Kahn processes, that could not be implemented with blocking reads, but were still monotonic. And he was a young researcher at a group in INRIA of theorists. And there was another Gerard that was more senior in the group. And so his boss didn't like the idea of having two Gerards in the group. So he called Gerard Gustav, just gave him a different name. And as a consequence, the function that Gerard discovered is known as the Gustav function. And it's a really pretty weird function. And I don't know if I want to do the aside to tell you about it, but yeah, I'm not going to tell you about it. I'll just hint at that there's a lot of pretty interesting literature there. A lot of it is, I guess it had the character of really being attractive to theoreticians much more than practitioners, okay, because there was this very beautiful mathematics behind it. And but it does have very practical realizations, and there are quite a few people who have really caught on to Kahn process networks. Interestingly, it seems like the context in which they've caught on the most has been actually in hardware design. So people design hardware systems, for example, for doing image processing chains using the principles of Kahn process networks. And it works pretty well in that context. But that's, in software, it hasn't done so well. And one of the reasons is really very simple. So if you have blocking reads, okay, this guy has to block whenever it calls read, then you have a problem, because suppose that you again have this scenario where this guy, when it receives an input, may or may not produce an output. So it checks some condition and it doesn't produce the output if that condition is not satisfied. Okay. Then should this guy do a blocking read? It could get stuck. Right? It could get stuck on this read and not be able to progress because that guy decided not to produce an output. So the essential problem with Kahn process networks when you try to use them for software is that you have to replicate your decision logic throughout your system and avoid doing the blocking read if that condition is not satisfied. And it better be the same condition. Right? That's analogous to this data flow situation where you had to use the same Boolean variable to represent the number of tokens produced and consumed here. Okay, so it's a replication of the decision logic that then has to get distributed throughout the system. So to me, this ended up being kind of a fatal flaw in Kahn process networks. And so we stopped working on them and decided that that was really not the right way to get deterministic concurrency. So synchronous languages are another very interesting alternative and still a very, very active area of research, even though these started also not much later than the Kahn process networks. I think the first synchronous language that really caught on was Lustre, which appeared in around 1986. And interestingly enough, Paul Caspy was the author of the Lustre language, and he called his language a synchronous dataflow language and published the first paper on it the same year that I published my PhD thesis on synchronous dataflow. And the two models of computation were completely different. But Paul didn't realize that. And so he kept citing my thesis as a synchronous dataflow work, claiming that it was essentially the same. So he never read my thesis, but he did cite it. He was a lovely guy. I really, Paul Caspy was wonderful, but he was a very generous guy. And, he was giving me credit for having contributed to his invention. And I didn't contribute anything to his invention. Okay, so one of the key ideas in the synchronous languages is to make the notion of the absence of a message as meaningful as its presence. And the key idea is, again, using this same cartoon of a program, is that you have a global notion of a tick of a conceptual clock. And at each tick, each connection has a value. Okay? Now, the situation gets particularly interesting when you have feedback loops. Okay? Because the value on the output of this guy can depend on the value of the input, which is the output of this guy, which depends on the value of these inputs, which depends on the output of this, which depends on the input of this, which depends on the output of this. Causality loop, right? But the synchronous languages resolve that in much the way that we do in Lingua Franca being able to execute when the dependencies allow it, and rejecting the program when they don't. Okay, so that concept in lingua franca is actually borrowed from the synchronous languages. And there's also some beautiful mathematics behind that. And by the way, my plan is in the last couple of lectures here to actually give you some exposure to that mathematical background. And I'm not sure whether you guys are interested in that. So maybe I should talk to a few of you and see whether you are or not, because maybe I should pick a different topic to talk about this last couple of lectures. But it's dangerous stuff to look at, because if you like math, it's really seductive. It's really quite beautiful. The reason that's dangerous is it can suck you in. I've seen it happen. I've seen people completely change their career path when they see it. But you have to really like math. I'll give you a little hint of what it's about. Okay. So here's a little feedback system that has 3 functions, and you can think of these as ordinary mathematical functions. That you know, this is a function that takes 2 arguments and produces a result. This is a function with no arguments and produces a result. So because it's a function, this is going to be just a deterministic result. Right? This is a function that takes 1 argument and produces a result. So given any such network of functions, you can always stack them up and create a new function, which we could call the yellow function here, okay, that takes 3 inputs and produces 3 outputs. And now that new function, f, has its inputs equal to its outputs. This is the synchronous principle in synchronous languages. It's not that this produces an output that is available next time the function is invoked. It's that the outputs of the function are also its inputs, okay, at a tick. So put another way, mathematically, if x is a vector with 3 elements, okay, then what this program says is that x equals f of x. The inputs are equal to the outputs. In math, this is called a fixed point. X is a fixed point. F. And a key part of the beauty of the math is determining what are the conditions such that there exists a fixed point and that it's unique. And if you have that existence and uniqueness, then you've got a deterministic programming model. Okay. So that's just a quick hint on that. So that's the principle on which synchronous languages are based, which is this notion of a single global tick. At each tick, every connection has one value, exactly 1 value. That value is the fixed point of a function. Okay. The function changes on the next tick, typically. So you calculate a new fixed point the next time on the next tick, and then you progress to the next tick. So it's the function that changes on each tick, not the values, right? The values are always the fixed point of the function. So lingua franca actually has exactly that principle, right? At each logical time, the value of all of the connections is the fixed point of a function, okay? A key difference between lingua franca and the synchronous languages is that we measure the time between ticks, and we give it a real-time interpretation. Okay, so each time logical time increments, you get a new tick. And in general, we call the model of computation that is that generalization of synchronous reactive, a discrete event model of computation. And you can think of it as a generalization of synchronous reactive where there's a notion of time between ticks. one of the problems, of course, with imposing a model of time like this is that you inevitably have multiple timelines, and this inevitably leads to confusion. It does even already in the synchronous languages. So for example, often when people talk about synchronous languages, they say, well, conceptually, every computation is instantaneous. Okay. And that's trying to get at this intuition that the input is equal to the output. But the instantaneity of the computation is actually not enough. And it's confusing to people because no computation is instantaneous. And so some people will just say, all right, that's an unrealistic model of computation. I don't have to pay any attention to it. And other people will say, well, even if it's instantaneous, that just means that the outputs are available instantaneously, but it doesn't mean that the outputs depend on the inputs at that instant. So this is this fixed point property. So to me, it's just not that useful. And the reason that people want to think of it that way is that they're trying to merge two timelines into one. They're trying to merge the physical timeline under which the computation progresses with the logical timeline of these ticks. And it's just better to keep those two timelines separate. They're distinct concepts. Okay. So discrete event models of computation are actually used in all kinds of frameworks. They're the basis for hardware description languages like VHDL and Verilog. They're the basis for network simulations. They're used a lot in large-scale simulation systems. I've seen them used in. I saw them used in. I think the weirdest application was in modeling the social dynamics of in Iraq of the formation of terrorist cells. And this was being done by constructing these big discrete event models of various interrelationships. And I don't know, I didn't understand it. It was a little too social sciencey for me, but it did get used in there. So lingua franca is actually a discrete event language in a manner similar to all of these, with interesting nuances. So for example, VHDL, have any of you used VHDL? Quite a few of you, okay. So VHDL actually has an odd sort of variant of superdense time in that, you have components whose outputs are conceptually 1 microstep later than the inputs without metric time increasing, which is sort of a curiosity of VHDL. But Verilog doesn't have that, and Verilog actually replaces that with non-determinism. And it accepts the non-determinism on the principle that hardware people don't care about that particular kind of non-determinism. And actually, it is kind of defensible in hardware design because the non-determinism shows up in hardware only as transient conditions, not as persistent conditions. Right? So that's one of the subtleties there. Okay, that's the whirlwind tour of deterministic models of computation. There are more, but those are the ones that I just wanted to give you some reference to and how they're interconnected. So let's stop there.